Welcome to the second talk in this series. This talk is covering the current, or like a very, very quick whistle-stop tour of the current prevailing theory of physics. And the idea of this talk really is to kind of lay some groundwork for things that will come later when we start ripping the current theory to pieces. So this is probably like the talk that I'm least excited about in the series, because it's more kind of like laying down foundations that we will then have fun with later. There's quite a lot to get through, attempting to cover all of physics in half an hour. So I might talk quickly, but hopefully not too quickly. And certainly when it gets into like all the different types of particles, if your head's spinning and you think, God, I can never remember that, don't worry. To some extent, the overwhelming complexity of the current theory is part of what I'm trying to convey. So if it's overwhelmingly complex, that's part of the idea. So the current theory of physics is referred to as the Standard Model, and the Standard Model comprises the theory of all the fundamental indivisible particles of matter, plus all the theories and equations that describe what those particles do and how they interact. So collectively, this is the Standard Model, and collectively it describes almost everything that happens in the universe. So you probably remember this old diagram from school, an atom which is made up of negatively charged electrons flying around the outside and positively charged protons in the middle, and neutrally charged neutrons that also hang out with the protons in the middle. So the electrons have a negative electric charge and the protons have an equal but positive electric charge. And so it is the electric force, with the law that opposites attract, that holds the electrons onto the atom and stops them pinging off into space. But you might be thinking, or you might have never thought, why do the protons stick to each other, given that they're all positively charged and they should be repelling and hating the shit out of each other, and yet for some reason they stick together? And the theory says that there is something called the strong force, which overcomes the electric force. And so despite the fact that protons want to move away from each other because of the electric force, the strong force is stronger, hence the name, and stick together. The force is strong, that is correct. So this strong force is another one of the forces from the Standard Model, and it is said that the strong force sort of operates through things called gluons, which get their name because they glue stuff on. The electron, which definitely looks like this, and you can buy one from particlezoo.net, is a fundamental particle. So you cannot split the electron down into smaller parts. So we call it a fundamental particle or an elementary particle. But the protons and neutrons are not fundamental particles because you can divide them down into smaller things. And those smaller things are known as quarks. Quarks look like this when they're fluffy. So there is an up quark, which has a positive charge, and a down quark, which has a negative charge. And the charges here, when we're talking about values of charge, are all relative to the charge of a proton or an electron. So the proton or electron charge is just given a value of 1, and then everything else is kind of relative to that. So the up quarks have a charge of 2/3, and the down quarks have a charge of -1/3. And they get stuck together in little bundles like this. So the proton is made of 2 up quarks and a down quark. And if you do the addition on the charges, 2/3 plus 2/3 minus 1/3 gives you a charge of 1, hence the charge of 1 for the proton. And the neutron is made of 2 down quarks and 1 up quark. And if you add 2/3 minus 1/3 minus 1/3, you get 0, hence the neutron has no charge. And the strong force, there are sort of two things that the strong force does, or two sort of slightly different operations of the strong force. One is to hold the quarks together into these two particles, and then the other is to hold these particles in bunches in the center of atoms. So the strong force is sometimes confusing because it does two separate things. And as mentioned, the strong force is mediated by gluons. But occasionally, as we know, atomic nuclei blow themselves to pieces. And this is known as nuclear decay. So it happens in various forms because the nucleus can come apart in different ways, sometimes emitting gamma rays, sometimes emitting a few neutrons and protons, sometimes emitting an electron, but they're all types of nuclear decay. And nuclear decay is said to be caused by the weak force. The weak force is the weak force because it's not as strong as the strong force most of the time. So normally the weak force is attempting to blow the atoms apart, but the strong force is hard as nails and it holds them together. But occasionally, under some circumstances, the weak force wins and an atomic nucleus gets blown apart. The weak force is said to be mediated by W bosons and Z bosons, which are like the arch enemies of the gluons, which make up the strong force. So they all kind of just do battle in the atomic nucleus. Now I've got a slightly more accurate diagram of the weak force, which looks like this. This is the weak force in action, blowing stuff up. So anytime you get any kind of nuclear explosion in the sun, in a power station, just general nuclear things, that is the weak force in operation. You can see those W bosons and Z bosons wreaking havoc there. But there is something else which is flying out of this explosion, other than the protons and neutrons being blasted out the nuclei. There is also these little guys called neutrinos. Neutrinos were they were initially theorized because somebody did some maths on some atomic nuclei blowing up and realized that the maths didn't quite add up and there must be something missing. There must be like some really tiny but very fast moving thing flying out that we were missing, because otherwise the numbers of what went in and what came out didn't add up. So someone theorized the neutrino, and after a lot of searching, because they're really, really small and have almost no mass and move really fast, we discovered the neutrino. So they have no charge, hence the name. They are neutral like the neutron, but they are tiny, and they have almost no mass. And so they don't really interact with anything. They don't really sort of interact much by gravity because they don't really have any mass. They don't have much mass. They don't have any charge. They're just incredibly hard to detect. And there are billions of them flying through your body possibly every second, at least every hour. They're just sort of incredibly numerous and they fly through the universe largely undetected. Now, according to the theory of the Standard Model, every particle is an excitation of a field for that particle. So essentially, quantum excitation, quantum is just meaning a specific quantity. So for example, with the electron, there is an electron field which permeates all of space. And if you excite that electron field to a specific quantity, you will make an electron. And if you excite the neutrino field to a specific quantity, you will get a neutrino. If you excite it not enough, you won't get one. So you have to excite each field to a specific quantity to get the particle of that field. So the up quark has an up quark field. The down quark is a specific excitement of the down quark field, same for every single particle. So down the left, we have our 4 fundamental particles that we've talked about so far. But if you sort of excite these particles more, or you sort of apply more energy to them, you can get them to kind of jump up to a second or third generation of the same particle. Now, these second and third generations are basically the same type of thing with the same electric charge, but with a larger mass. So the up quark has a sort of larger sibling called the charm quark, and the down quark has a larger sibling called the strange quark. The electron has a larger sibling called the muon, and the neutrino has a larger sibling called the muon neutrino. And then if you get matter really excited, there's this sort of third generation of these even more massive particles. Again, they all have the same charge as their siblings, but they are more massive. These particles don't generally hang around. You get them in sort of situations with really high energies. You might get them in a particle accelerator, or I think you sometimes get them generated in the upper atmosphere, but generally they decay very quickly. So we mostly know about them because we've worked out that they must exist from the things that they decay into. But you don't see them hanging around much, but they exist. Oh, yes. I'm pressing for the next slide. And what is actually appearing are the little charge numbers down the right-hand side. So all the things on the top row have a charge of +2/3. All the things on the second row have a charge of -1/3. All the electron type things have a charge of -1, the same as the electron. And all the neutrino things have no charge, they are neutral. So those are the particles that we would call matter. But there are particles that we've also mentioned, like the gluon and the W boson and Z boson, which are particles, but they are force-carrying particles rather than matter. So the gluon glues stuff together, Z boson and W boson blow stuff up. And then the photon is also considered a force-carrying particle. So collectively, they all make up this lovely table of the standard model of fundamental particles. So everything you see in this table is something that we have just covered. It's essentially that same group of all those particles. But there is one more thing, which is this Higgs boson stuck on the top right-hand side. And to understand what the Higgs boson is, we need to ask another question. The question is, where does mass come from? So all of those particles, such as the up quark and the down quark and the electron and the neutrino, all have some amount of mass. The question is, where does the mass come from? But to answer that question, we have to answer another question. Sorry, to answer that question, we have to ask another question, which is, what is mass? And mass is not, contrary to what we sort of commonly think, mass is not the amount of stuff. Mass is a behavior of stuff. It is the property of stuff, which is the behavior that if you try to change its speed or direction, it is the extent to which it resists that change. So if you've ever tried kicking a brick, you'll realize the brick has quite a lot of inertia, which is why your foot hurts. And this is where we get this famous little equation at the bottom, F equals ma. The amount of force required to change the speed or direction of an object, in other words, to accelerate it, is proportional to the mass of the thing that you're trying to change the speed or direction of. So it's not a measure of the amount of stuff you have. It is a measure of the extent to which that stuff doesn't want to change its speed or direction. Mass is not the amount of stuff. And the standard model solves this problem by introducing the idea of another field on top of all the different fields for all the different particles. It introduces another field, which is like a sort of sticky treacle field, which just kind of attempts to attach itself to all the other particles and slow them down. This was the best analogy I could come up with. This is the Higgs field, and whenever you try to accelerate your car, the Higgs field just kind of hangs on and tries to slow it down. I also think the gaffer tape analogy works quite well because it's just sort of stuck onto the edge of the standard model theory of like, what about this mass thing? I don't know, just add on another thing and that'll fix it. And we will come back to this in a later talk and look at a completely different explanation for what could be causing mass. But in the standard model theory, all particles interact with the Higgs field, and the Higgs field slows them down. It should also be clarified that the Higgs field and the Higgs boson are two separate things. The Higgs boson is the quantum excitation of the Higgs field. So if, like with the electron, if you get the electron field excited enough to a specific quantity, you'll get an electron. If you excite the Higgs field to a large enough quantity, which is a really large quantity, you will get a Higgs boson, which is the particle of that field. But in general, the Higgs field just goes around sticking itself to stuff. So that now completes our discussion of all of the elementary particles of the standard model, all 17 of them. And so we can now look at what is the theory of what these particles do and how they behave and how they interact with each other. And that is all explained using a simple equation, which looks like this. Obviously, I understand this perfectly and could definitely explain it without any problem, but we don't have time, so we'll have to move on. But there is a simplified version of this equation, which I assume is just that they've taken some of the large numbers of symbols and condensed them down into one symbol to represent a lot of things. So this is kind of simplified, condensed version of the equation, which I think is worth looking at, only to understand that the current standard model of physics has lots of separate parts to it which are not compatible with each other. So quantum mechanics, which is essentially the study of everything smaller than an atom, is a completely different set of theory and explanations to gravity. So we have an explanation for gravity and how that works, but it kind of completely breaks down when you get down to things smaller than an atom. And the theory of matter is its own thing, but we've had to stick the Higgs boson on separately to explain the mass part of it. So the takeaway from this is just that the standard model is a set of slightly separate theories, which when you stick them all together, account for everything that we see. The other thing which I haven't mentioned is antimatter. Antimatter is confusingly named, slightly confusingly named, because it is not anti-mass. Antimatter is just the idea that for every one of the matter particles, as opposed to the force-carrying particles, there is the possibility of having the same particle, but with the opposite charge, the opposite electric charge. So antimatter particles all have the same mass, but they are just the same particle with the opposite charge. So the up quark has its evil cousin, the anti-up quark. The charm quark has its evil cousin, the anti-charm quark, same mass, opposite charge. And so the pattern continues. The down quark has an anti-down quark, strange quark has an anti-strange quark, the bottom quark has an evil cousin, the anti-bottom quark. Same with electrons, but it's not called the anti-electron, it's called the positron, just to be confusing. They all have their evil anti-charged particles, except the neutrinos, because the neutrinos do not have any charge. And because antimatter is actually anti-charge, the neutrinos are their own antiparticles. They don't have any opposites. Antimatter doesn't hang around because as soon as any particle meets its own evil cousin, the two particles just annihilate and you just get a bunch of photons flying out as energy. So antimatter has been created and it can exist, but as soon as you create it, as soon as it touches a piece of normal matter, it just annihilates and you just end up with energy again. But that is worth talking about. So I'm now going to, with all the kind of particles and all the bosons and all the things covered in their array of complexity, all 17 of the fundamental particles of the Standard Model, its crazy equation, and the idea of antimatter. And I want to look at two of the really key pieces of theory which are part of that Standard Model equation and which give us some really, really successful laws of physics, which sort of make up a really key part of our physics theory. These two laws were created by this guy, who you probably recognize. He created two separate theories, both called relativity. The first one is the special relativity, and it's called special because it's kind of the special case. And then it took Einstein 10 years to come up with the general case, which is the more complete version, which is like the generalized solution for how stuff behaves. So take a quick look at special relativity, and we touched on this slightly in the first talk. Relativity fundamentally says that all places in space are relative and all forms of movement are relative. You only know that you are moving relative to something else. And special relativity says every frame of reference is equally valid. You can't ever say that you are still or you are still. It just depends whose perspective you're looking at it from. As mentioned before, time appears to slow down the faster you travel, or at least it appears to slow down from the perspective of somebody else who is considering themselves stationary. If you travel so fast that you reach the speed of light, time will actually stop. And I don't know quite what analogy I was going for here, but something about the fact that if you run off the cliff at the speed of light, time stops before you fall to the floor. So this is where the idea that if you go faster than the speed of light, you go back in time comes from. Because as time slows down, as you get faster and faster and faster, and it in theory stops if you get as fast as the speed of light. In theory, if you carried on getting faster, time would go backwards, although nobody's ever achieved that, so it's only theoretical. So special relativity says that in the normal case, the speed of one thing is relative to the speed of another. So if I'm stood stationary on the carpet and I'm looking at the speed of the cat and the speed of the mouse, the speed at which the cat is approaching the mouse is the speed of the mouse relative to the carpet minus the speed of the mouse, minus the speed of the cat relative to the carpet. This is just how we expect everyday life to work. If someone throws a cricket ball at you at 20 miles an hour and you run away from it at 10 miles an hour, it only hits you at 10 miles an hour. This is just normal behavior of things in the way we expect them to work. But there is one exception to this, which is light. So the speed of light is constant for everyone, no matter whether they are moving or not, and no matter whether they are moving according to their own frame of reference or somebody else's. It doesn't matter where you are or whether you're moving, light will always approach you at the speed of light. I've got another way of describing this because I think it's an interesting concept and it's worth sort of looking at it from a couple of angles. The first angle is that the death ray laser will always get you. But another way of looking at it is this. So if someone is standing shining a torch towards a brick wall, then from the reference frame of the brick wall, that light is approaching the wall at 300 million meters per second, which is the speed of light. That makes sense. That seems normal. But if this person is standing on a really fast skateboard and they are traveling towards the wall at 1,000 meters per second, then the light is traveling away from them, out of their torch, at 300 million meters per second. But they are moving forwards towards the wall at 1,000 meters per second. So surely the speed of the light towards the wall must be the speed at which it's going out of their torch, plus the speed at which they're moving towards the wall. But that's not correct. The speed of light out of the torch is 300 million meters per second, but the speed of light towards the wall is exactly the same, which is just weird. And this is one of the key sort of tenets of special relativity, is that the speed of light is constant no matter who you are, where you are, or how much you're moving. And the theory kind of says that the universe translates between reference frames because the reference frames just disagree with each other. So there must be this kind of somehow translation happening by the universe so that the speed of light appears the same for everybody. And one final piece of special relativity is that objects contract the faster they travel. And this is from the point of view of a static observer. To somebody in a space rocket, everything will look the same as it normally does. Everything will look the same shape. But from a static observer, an object traveling at very, very high speed will shrink in the direction of travel. So that is special relativity, which was Einstein's first great theory. Everything is relative. There is no single static reference frame. Every frame is equally valid, but the speed of light is constant for everybody, and the universe translates between those reference frames. And objects shrink the faster they go. So that's the first set of weirdness. But Einstein later, Einstein later combined special relativity into a more generalized theory to include gravity. So this is general relativity, and it involves a lot of complex equations, which I don't claim to fully understand, but I'm just going to give a quick overview of the basic sort of concept of general relativity. General relativity says that there is this thing called space-time, and that mass causes it to bend. You might sometimes hear physicists talk about flat space, and what they mean is space which is not distorted by having mass in it. So there's this idea that the Earth is huge mass, it causes space-time to bend, and therefore if you were to imagine rolling a ball across this surface, the ball would fall in towards the Earth, and hence objects fall towards the Earth. There's a slight difficulty with that explanation because the explanation relies on the idea of things falling down into that dip, which relies on the idea of gravity to start with. But this is the concept. The idea is that matter bends space-time. If you were to look at that in 3D, it might look a bit more like this. So that would be the Earth in the middle, and then what was flat or straight space gets curved because of that mass. This is general relativity in a single sentence. Matter tells space-time how to curve, and that curved space-time then tells the matter how to move. This theory is just incredibly successful at predicting things. So I just want to cover a few of the things that were predicted by Einstein's general relativity, which turned out to be true. The first is black holes. The theory says that if you get enough mass in a small enough space, it will bend space-time so severely that nothing will be able to escape, not even light. This idea didn't exist until general relativity. It was a prediction of general relativity. Einstein nor anybody else had ever seen a black hole or seen the black space where a black hole must be. until after he created this theory. So he predicted black holes, and we've later shown that they do exist, and that is correct. General relativity also predicted that if you have something like this, which I think is a galaxy, and you have other stars or galaxies behind it, that the light will bend around the galaxy and you will be able to see it in front of it. So that ring, that blue ring you're seeing, is light coming from behind that galaxy, being bent by the galaxy and coming back around towards you. So Einstein predicted these, what we call Einstein rings. He predicted them, nobody had ever seen them. It turns out they are a thing. He was correct. This is a really bad diagram of the solar system, which is not at all to scale, but it's here to remind me to say that general relativity predicted the orbit of Mercury. And the orbit of Mercury is kind of complicated because you've got Venus and Earth and the other planets interfering with the gravity and pulling it in slightly different directions at different times. And there are a few other factors that come into it. And Einstein's theory of relativity predicted a slightly different orbit for Mercury than the one that was previously predicted, which was done by Isaac Newton. Turns out Einstein's prediction is correct, not Isaac Newton's. So again, general relativity just proved to be the correct set of calculations. It's also been shown that it correctly predicts not only the orbits of satellites, but it predicts the extent to which time slows down the closer you are to Earth. So one part of general relativity is that because mass bends space-time, time runs slower the closer you are to a large mass. So the clocks on Earth run slower than the clocks in satellites. And when we first deployed GPS satellites, the software developers put a switch in the software that was like the Einstein switch, because nobody was quite sure whether Einstein was correct or not. So if he was correct, and if time slowed down on Earth compared to in space, the way that Einstein predicted, we would need one set of calculations in the software. And if Einstein was wrong, we would need a different set. So they put like a general relativity switch into the GPS software. Turns out Einstein was absolutely correct, and none of our GPS software would work if it wasn't for his calculations from general relativity. So just time and time and time again, general relativity keeps on being subjected to experiments, and it keeps on being correct. With a couple of exceptions. One exception is when you get to quantum mechanics, i.e. things smaller than an atom, it all breaks down, doesn't work. And the other one is when you get to really big things, e.g. galaxy scales. As we talked about before, there's this idea of dark matter, that there must be some extra matter because the calculations you would get from general relativity give you totally the wrong prediction in terms of how fast a galaxy can spin without flying apart. So general relativity is incredibly successful, except for really small things and really big things. So that brings us to the end. Quick whistle-stop reminder of the standard model of physics. Quarks, electrons, and neutrinos are the fundamental particles of matter. There are 7 fundamental particles in total when you include all the force-carrying particles, which stick things together and blow stuff apart. The Higgs field is like a sort of treacle field that slows stuff down, creating the behavior of mass. Antimatter is just normal matter, but with the opposite charge. Special relativity says all frames of reference are equal, universe translates between them, time slows down the faster you go, speed of light is constant for everyone, objects contract as they travel faster. General relativity says matter tells space-time how to curve, and curved space-time tells matter how to move, and that predicts almost everything we see. that is the end of this talk. As I mentioned at the beginning, this talk is very much the sort of laying the foundations for us being able to dig into this and ask some more interesting questions about it and really start to rip it to pieces in the subsequent talks. So that is it. I apologize for having left a huge amount of time for questions. There was a lot to cover in that. And in the next talks, we will really sort of dig into some of the more interesting stuff and start to rip this apart and really get into the fun. So that is it. If you